I'd like to spend a little time talking about attachment systems, kind of to bring us this idea of the concept of thermal breaks. Um, One of the issues with our contemporary thinking on high performance buildings, problems or issues that's coming up is this idea that we leak energy. We transfer energy through conduction from the inside of the building to the outside of the building by the framework, those clips and attachment systems that we use to hold our facade on. And the reason it's becoming more important is really not that the buildings are leaking more energy that way, but because it seems to be more of a significant part of the energy consumption. So if we were to look at, if we went back in time and looked at how we thought about energy loss in buildings, in older standard performing buildings, I have a big box of total energy loss. And then that little red box is energy loss by thermal conduction, that movement of heat along the clip systems and rail systems that we attach on the exterior of the building. And then today, with newer, higher performance buildings, by the increase in insulation, the tightness of the building, our total energy loss is much less. But our energy loss by thermal conduction hasn't changed. So it appears to be a more significant component in energy loss of our facade systems, and therefore a focus of more attention. And so it's not uncommon that as we create higher and higher performing systems, that these little details become more significant. And that's in fact with what's happening with our clips and attachment systems. And this is also called this idea of these thermal conductions out, our thermal bridging. Here's some illustrations about the way that the attachment systems are actually leaking energy to the exterior and or transferring energy to the interior, depending on which way you're looking at it. And so one of the ways we're addressing that issue currently in the construction of these systems is this idea of the incorporation of thermal breaks. So here we have the metal attachment system, and then before it touches the interior wall surface, we have some material that's not a good conductor of heat, whether that be some sort of plastic and or phenolic. There are a few different kinds of materials that both have good compressive properties and significant resistance to heat flow. So I think it's important that you understand this concept of thermal breaks and how that's affecting the way we're thinking about kind of wall systems in and of itself. Here's another one that I got from one of those seminars where we're moving with exterior insulation systems, kind of thinking around that idea about that break in the wall, that thermal conduction out. We have just the evolution of wall systems, where we're actually moving the insulation from the inside of the cavity to the outside wall system, where we have our water moisture barrier underneath, or our air and water barrier underneath our insulation as we currently do. And then this final one is this idea of continuous insulation with an outboard water resistant barrier to it. And this is heavily proposed by this Atlas vendor who made a presentation. There's a lot of sound reasoning behind that. The idea of having that air barrier on the exterior where any penetrations can be addressed and sealed and be visible and not hidden under insulation is a relatively interesting concept. But once again, I caution you, I don't know whether this will become an accepted method of construction, but we're really kind of violating in this evolution as is proposed here, the idea that the insulation is something that could get wet, that moisture will always go through that barrier. And if it does get wet then, and it's covered with the air barrier, how will it dry out? So, throughout your career, you're going to find conflicting ideas about the way wall systems and these kind of systems perform. And it's really left up to you and your facade consultant to pick what you think is the most effective and sound construction methods for your area, for the techniques that you're using for construction. Some more ideas about these kind of clip systems. So even if you come up with your own facade material and want to attach it, there are many clip systems that are now currently available that will allow you the kind of flexibility to create any kind of rain screen system you want. So this is just a screenshot again. And if you look at the bottom left-hand side here, you can see how they make clip systems for all kinds of thicknesses of insulation levels and the amount of offset that you would want for your facade. I'm just showing you, these are just the kind of technical details that would be typical in a set of CDs about the way you deal with the kind of details of hanging the facade on the building. In this case, it's that return back to the window and how that's supported and how that joint looks in that detail. And this is actually from, I guess, researching on one of the punch facades that uses terracotta material. Just some interesting illustrations about what these technical details look like. So if you look over my head, you can see, directly over my head, you can see the floor assembly in that front elevation. You can see the clip at that floor assembly, and then supporting a larger bracket that actually supports that tile. And then above the tile, you can see that triangular piece that is kind of the sill plate for the window assembly. So you can study these drawings and really garner a lot about the methodology of detailing these kind of systems. I want to direct, because we talked about this idea of materials and then the embodied energy, this is hyperlinked. This will take us out to a site. Let me see if I can click into this quickly. This will take us to, let me adjust this and move up closer here. This takes us to an interesting site that allows us to do kind of an analysis of embodied carbon, especially in this idea of exterior envelopes and those assemblies. You can go down, and this is a life cycle assessment, which is that idea about both embodied carbon and operational. And actually what they do is they talk about this kind of an interesting illustration, but we have the idea of a conventional building built to code, operational energy, a larger part of embodied energy. But just as I said with the idea of that, the thermal breaks and significance, as our buildings get higher and higher performing, they're needing less operational energy, and that embodied carbon becomes a significant factor in the overall environmental impact of the building. So this goes down and really kind of goes through a lot of this idea of these building systems, and then eventually leads you to the ability to use their calculator. And I'm not finding it right here right now. Maybe if I go to, yeah, here we go to the envelopes. So we have global warming potential. We could have life cycle, all impacts, lifespan, pick your lifespan. I'd have to research what they mean by biogenic carbon. But here we have global warming potential of different materials. And once again, we discussed that idea of that very thin granite limestone kind of materials and what their carbon footprint is. You can see that some of these are really kind of off the chart. But remember again, though, that these are also now cut very thin, but they're applied to high-tech materials. So their analysis about their global warming potential can be quite varied. We have, so some of this makes a lot of sense. So we have a spandrel aluminum with a backpan being probably the most potential for global warming with CO2 emissions because we're using aluminum. If we move to wood, it has the least amount of effect. Steel, much less energy intensive than creating aluminum, a lower kind of environmental impact. And we look at, here we have glass reinforced concrete. Glass fiber reinforced concrete makes a really quite a large variety of the kind of facade decorations you can make, but it really has a high environmental impact. And obviously at the bottom, this idea of wood. And I'm looking for terracotta. And once again, like I said, this does not necessarily have the best kind of carbon footprint when compared to some other materials you might choose. And then you can go ahead and select your materials and then select the amount and create a calculator based on that to do an analysis about why you make a decision on the footprint, the carbon footprint of the facade you've chosen. This is kind of a side point to this, but I still think it's quite significant. Ventilated facade systems can help save energy over a conventional wall because of this decoupling of the surface heated by the sun. So this is an examination of NASA's one of their masonry buildings. They had no facade on it at all. They looked at the energy use. It's the blue bar. And then what they did is they put a facade on it, a ventilated facade system, and that decoupled. So you have the interior surface of the wall, and then you have the facade. And in the first case, the facade could be considered touching. And when we decouple that and pull that away, now any sun that's heating up this facade is not directly heating up the interior wall. And as a matter of fact, when this facade gets heated, air moves through this channel, because as air gets warmer, it becomes lighter and moves up. So there's this air convection through there. So we're actually cool. We're bringing cool air between the hot facade that's getting exposed to the sun and what we hope to be a cooler interior wall. So in fact, in warm climates with a lot of solar insolation, a lot of sunshine on wall surfaces, ventilated facades can save significant amounts of energy in heating, or excuse me, cooling loads. So I thought that was a really quite interesting thing to keep in mind. We'll pick up on some examples of punched facades next.